Hello everyone, welcome back to Under the Apple Tree, and today we're going to be going over some related rates. Now, if you're here, it's probably because you're really frustrated with related rates, and the reason that I think that is because it's the first time you really have to do any sort of applied calculus. You're given a derivative, you just learned how to do derivatives, and now you're being asked to apply derivatives to real-world situations, and oftentimes you have to bring in another formula like volume or surface area, or the Pythagorean theorem in this video. That's what we're going to see. And let's go ahead and just jump right in. The best way to get good at this is just doing examples. So let's start with this question. An oil slick has formed whose volume increases at a rate 200 cubic centimeters per minute. The oil slick takes form of a right circular cylinder with both its radius and height changing with time. It's actually really important that it's a right circular cylinder because we can use, equations for cylinder, volume, area, whatever. If it's not right circular, then you cannot solve this problem. Your teacher might tell you to assume it's right circular because there's really no way to solve it without it. So let's go ahead and draw our cylinder. Just a rough sketch so we have something to look at. And so it said height and radius are changing. So here's our radius. Here's our height. It's pretty bad drawing, but you get the idea. Volume is increasing, and the height and radius are going to be changing with time. We don't know exactly how yet, so let's keep reading. The instant when the radius is 50 centimeters and the height is 0.2 centimeters, the radius is changing at a rate of 0.25 cm per minute. So what this means is they're basically giving us dr dt, and he's giving us like the parameters for when that rate of change. So we know that at that moment r is equal to 50, and we know that height is 0.2, and so the rate of change is just going to be 2.5. So this is a lot of information. This is going to be very useful. Alright, let's keep reading. At this instant, what is the rate of, that should be rate of change, excuse me. Rate of change if the height with respect to time. There's a couple typos in there, but what is the rate of change if the height? What is the rate of change of the height with respect to time? Sorry about that. Alright, so basically we need to find dh dt. What is dh dt? And since it's at this instant, the same instant that we're given dr dt, we know that this is the instant when r is equal to 50 and when h is equal to 0.2. Okay, so this is a lot of information. We were also given, I forgot to write it down, we were also given dv dt. dv dt equals 200. So where do we go from here? We really have no way to connect any of these three derivatives, and so what we're going to have to do is use an equation. And since they're just giving us dv dt, we know volume is the way to go. So what's the volume of a cylinder? And you've probably all forgotten about like the volume and area equations, and that's why related rates is such a pain for so many people. But if you do it long enough, you'll remember. The volume is just pi r squared times h. But if we read the question again, nowhere in there does it give us any information about volume. All we have is how the volume changes, the rate at which volume changes, dv dt. So we're going to go ahead and take the derivative of v. dt. And we have to take the derivative of everything with respect to t. So take the derivative of, so this part is what confuses a lot of people, so I'm going to explain it and go through it pretty slow actually. So in this equation, pi r squared h, there's two variables that are always changing, r squared and h are always changing. So think of them as different variables. Usually x and y are what you're familiar with if you're doing differentiation a lot. R and H are the two different variables in this situation. So we're going to handle them separately. We're going to do like a product rule type thing. So we have to do them separately. So you need to think of it as. Okay, so the first one, derivative of pi r squared is just 2 pi r. And since this is like implicit differentiation, we're going to have to add in a dr dt. dt, and then times h, because in product rule, the second part stays the same. So yeah, this is why related rates are so hard, in my opinion, because you use so many things, different things that you've learned. Now we have to take the derivative of h. So pi r squared stays the same. Pi r squared. Now take the derivative of h. Derivative of h is nothing, right? Because it's just a single variable. Like derivative of x is 1. Derivative of y is 1. Same thing. Derivative of h is 1. But we do have to put in the dht. dht. Okay. So this is our rate of change formula, the volume. Now, how many unknowns do we have? Well, dvdt 1, r 2, drdt 3, h4, dhdt 5. So let's see what we can plug in. Well, we have dvdt, so we can put a check mark there. Boom. R, yes, r is going to be 50 at this instant. drdt, yep, it's going to be 2.5 at this instant. Height, going to be 0.2 at this instant, yep. R did radius, dhdt, that's what we're solving for. It looks like we're in good shape. We can solve this equation. Sometimes you're going to have two unknowns. You're going to have to use like another formula to find that information. I'll give you an example of that in the next example problem. Okay, so let's go ahead and just start plugging in numbers. 200 is our dvdt. We got that from up here. It's going to be equal to 2 pi r. R is 50. drdt 2.5 h 0.2. So what you guys are probably going to realize here is this is the easy part, plugging everything in and doing the algebra. It's setting it up is what's difficult. So once you get it set up, you're probably going to get the majority of the points if it's on like an exam or homework, because that's the hardest part. And then dhgt, that's our variable. That's what we're solving for. Okay. So now we're going to have to work out some math here. This all reduces into, let's try 200 first. 200, that's all going to equal 50 pi plus, this is square. I forgot to square the radius here. Sorry about that. 50 squared is just 2500. Pi times dhdt. Then we're going to go ahead and move some stuff around so we can isolate dhdt. So you would subtract 50 and then divide by 2500 pi. So what we're going to get is dhdt 200 minus 50 pi all over 2500 pi. And then we could pull out a 50 and reduce everything, and then you would get 4 minus pi over 50 pi. But this is also correct. It's the same rate. Okay, so let's move on to the next one. I hope everything was clear, easy to understand in this one. It helps to draw a picture. It helps to write down everything you know and you don't know, like I did here. This is really useful. So the next one. A rocket is rising vertically and is being tracked by a radar station. on the ground 5 miles away from the launch pad. How fast is the rocket rising when it's 4 miles high and its distance from the radar station is changing at a rate of 2,000 miles per hour? Okay, so let's draw a picture. So the rocket is flying somewhere in the air. A rocket. It looks more like a UFO, but you get the idea. And it is just, here's the launch pad. And here's the station. And so the radar station is 5 away from the launch pad. And it is, what other information did they give us here? 5 miles away from the launch pad. Let's call this distance y. Y is constantly changing, so we're going to put it in as a variable. And this distance here we're going to call r, so another variable. And so the shape we're dealing with now is a triangle. Last time it was a cylinder, this time a triangle, so hopefully you're a lot more comfortable with the type of equations we'll use, because I would think triangle is a lot easier to deal with than a cylinder. Okay, how fast is the rocket rising when it is 4 miles high and the distance from the radar station is changing at a rate? So distance from the radar station is r, and y is 4. How fast is it rising? How fast is it rising? Well, that's dy dt. So what is it? We need to know what that is. The parameters they're giving us, 4 miles high, y equals 4. And dr dt is equal to 2,000. And that's at the same instant when y equals 4. Okay, this is the information we're given, and you notice it's actually a lot less information than in this cylinder question. Look how much I had over here. I think the reason is maybe because this is a two-dimensional problem, and the equations are a lot smaller, easier to deal with. Anyway, let's get into this. So the equation for the triangle we're going to be using is the Pythagorean theorem, since the legs are changing. Let's go ahead and write that down. Y squared plus 5 squared. There's no need to give this 5 value, this value here from the launch pad to the station. We don't have to give that a variable because it never changes, so we'll just keep it as 5. And then equals r squared. Easy enough. And then, so if you look at all the information we're given derivatives, we're given rates of change, dy dt, dr dt. So what we need to do is take a derivative of this. And what derivative do we take though? Do we take d dt, d dy, d dr? There's kind of a lot of options, and it's kind of overwhelming. And I think this is another one of the things that confuses people, but you just need to remember these things change with time. If time were to freeze, these things would not change. So if it's a related rate, you're just going to do d over dt. It's a good tip. It's going to help a lot. D over dt. Now we take the derivative of everything. It's the derivative of 2y, or of y squared. I already said the derivative. It's 2y. And now you're going to have to write dy dt. dy times its rate of change. What's the derivative of 5 squared? 0. What's the derivative of r squared? 2r. And we're going to have to do the derivative again, or the rate, dr dt. Let's erase it. Redo that r. dr dt. Okay, so this is the equation we have right now. And so let's look and make sure we have all the information we need. So a y, do we have a y value? Yes, y equals 4. dy dt, we're solving for that. That's a variable. Of course we don't have it. R, we actually don't have an r value, so we're going to have to find that. And dr dt, 2,000. So we have two unknowns, only one equation. That means we either need another equation or some way to solve for this last variable. And fortunately for us, this is a triangle, and we know the Pythagorean theorem. So 5, this one's 5, it never changes, but if you notice, this is at the instant when y equals 4, so this is no longer a variable, we know it's 4. So now we just do the Pythagorean theorem to find the r at this instant. So we'll have 5 squared plus 4 squared equals r squared. 5 squared, 25, plus 4 squared, 16. 25 plus 16 is 41. Equals r squared is going to end up being square root of 41. Okay, now we plug that in here. And so now our only variable is dy dt. And that's what the question's asking for. Perfect. So our y value is 4. dy dt is our variable. 2 times r, our r is root 41, we just solved for that, times dr dt, which is 2000. Now we solve for dy dt. This point is just algebra. We've already done the hard part here at this point. I'm not even going to walk through the algebra. I'm just going to tell you the answer. It's going to be 500 root 41 miles per hour. Okay. So yeah, it's just you have to write down the information they give you. Changing at a rate of 2,000 miles per hour, the distances, so you write that down, dr dt 2,000. At what instant too? It's also really important to write down at what instant it is, so you can see these two are related, and when I put them both in an equation, I can use y equals 4 in that equation. These very small details of writing down and setting up the problem that make solving the actual problem so much easier. That's going to wrap up this video, guys. I hope you enjoyed it and learned a lot. Good luck on all your exams. I'll see you next time.